I'm Jing. I'm working on Project 8, Bus Prototyping or LTE Mobile Terminal Radio Transmitter on FPGA. The sponsor is Calit-2. Today I'm going to go over this project in the following aspects. First is the introduction, and then the simulation results, and the DFT algorithm and hardware design plan, and finally it's the conclusion. Okay. In this project, we focus on the uplink channel, and this block diagram shows the structure of the uplink transmitter. We call it a single carrier FDMA. The structure difference of single carrier FDMA and the traditional orthogonal FDMA is this endpoint DFT block. In single carrier FDMA, both DFT and the inverse DFT are employed in both transmitter side and the receiver side. In LTE, this N is limited to the products of integers 2 and 5 and 3. Also, N is bounded to certain range, which is determined by the bandwidth of the channel. Here, this 12 is the number of the subcarriers per resource block. And for this frequency domain subcarrier mapping, we have two different mapping models. One is distributed model and the other is localized model. In LTE, we use localized model to achieve a lower PAPR. The problem is why we choose single carrier FDMA in LTE. This is because single carrier FDMA has the following principal advantages over orthogonal FDMA. First one, single carrier FDMA has lower PAPR, which means the single carrier FDMA has lower power consumption at the mobile terminal side. And also, this single carrier FDMA can guarantee a lower complexity and high quality equalization at the receiver side. Also, single carrier FDMA has flexible bandwidth assignment. Next, I want to show some basic 3GPP LTE standards. Here is the resource grid. One radio frame is divided into 20 time slots, numbered from 0 to 19. In the time domain, each slot contains 6 or 7 symbols, which is determined by the model of the cyclic prefix. And in the frequency domain, one resource block contains 12 subcarriers. Those subcarriers are equal spaced. That's to say, for one resource block, in the frequency domain, it's 0.5 milliseconds, and in the frequency domain, it's 180 kilohertz. And here is some bandwidth and resource configuration. We can say for LTE, the channel bandwidth switches from 1.4 megahertz to 20 megahertz. And here is a simulation result of a specific 5 megahertz system. And with all those assumptions are based on 3GPP LTE standards. And those two figures shows the PAPR property of both single carrier FDMA system and orthogonal FDMA system. The X is the PAPR in dB, and the Y is the probability of PAPR greater than certain value. For example, for the single carrier FDMA, the probability of PAPR greater than 6 dB is about 0.05, and that's for the orthogonal FDMA, it's 0.5. So we can say single carrier FDMA has pretty lower PAPR. Okay, I claimed in LTE, N is limited to the products of 2 and 3 and 5. But we know in the MATLAB, the FFT block, the size of FFT is constrained to the power of 2. So when we do LTE Simulink, we cannot directly use the FFT block. So I tried to design a different block to realize a combination redux DFT processing. Here, those steps shows the basic design idea. Firstly, we factorize the size n equals to a times b, then perform b times a DFT. Here, this a make it equals to 2 to the power n, so we can perform radix 2 DFT. And then we multiply the outputs by different Twiddle factors, and then we perform a times b DFT. And here this b can be further factorized into another 2 numbers, so we can repeat this the split radix DFT, and finally realize a combined non-radix 2 DFT. And here I show example. This is a butterfly or n equals 60. So first I factorize 60 into 4 and 15. So firstly I perform 15 for DFT, and then multiply the outputs by different Twiddle factor, and then perform for 15 DFT. Actually, this 15 DFT is a combination of 5 and 3 DFT. Okay, and then this is a Simulink example for n equals 12, and the inputs are random complex numbers. Okay, I do this simulation and got those results. But for all those examples, we have fixed date inputs. But our final goal is to realize a variable data length and a complex radix DFT transform. So we need to add some logic control to those blocks, but I haven't figured out how to realize this. Okay, this is my project.
So we think of the standard FFT as growing as kind of order n log n. Can you say anything about either
the complexity, right?
Yeah, the complexity. Can you say anything about how it grows if you apply your factorization?
I think it probably is in the same level. It's all the small prime DFT. The smaller, the easier. That's why we choose it's really 2, 3, 5, not a lot of some bigger prime numbers.
Anybody else have any questions?
Okay, thank you.
Okay, we group 3, and we're back to